But I'm going to use the same reaction and the same value of K just for simplicity's sake. Okay, so the things that I'm going to change are our values of H2, I2, and I'm going to add in let's put some values in here. So I have the HI is 0.5, the H2 is 0.1, and the I2 is 0.05. Okay, now that's easy enough. I can put my initial concentrations in here. However, when I go to determine which direction the equilibrium is going to shift, I don't exactly have an answer. I don't know which is going to be positive or negative. So we're going to find something called the reaction quotient Q. Now, the difference between Q and the equilibrium constant is that Q is not equal to our equilibrium constant unless our situation is at equilibrium. Okay, let's see what Q is for this case. So HI squared, this is 0.50 squared over 0.10 and 0.050. So somebody calculate for me this value. So everybody should go through the calculation. So do you have it, Luke? 50? I messed up. Put it too close to equilibrium. However, it's not quite equilibrium, right? Okay, let's do something. All right, forgive me for this. Because I made it too close to equilibrium and I've only got two significant figures, I'm going to change this up a little bit just to mess with everybody. We're just going to make that 0.40. Okay. Which then is not going to be 50 anymore. It's going to be smaller than 50, right? There, that's better. 32, right? Okay. Now, knowing the value of Q, is Q smaller or greater than our equilibrium constant? In this case, it's smaller. If it was greater, this side would be negative. But as it's smaller, it's going to shift to the right. If it's less than our equilibrium constant, it's going to shift to give us more product. If it's greater than our equilibrium constant, it will shift to this side to give us more reactants. So Q can tell us which way the equilibrium is going to shift. In this case, it tells us that these values are going to be negative and that value is going to be positive. Okay. At this band 0.6 instead of 0.4, I would have the values the other way. Now, it doesn't really matter. I just picked this particular one because it was simpler for me to do the calculation. All right. Now, our change is still going to be the same. Why? Well, I already know, having calculated Q, that these are going to be a decrease. And our coefficient is still 1. This is going to be an increase. Our coefficient is 2. However, when I do this, now again, go ahead, realize there's more significant figures. I wrote it this way to simplify it a little bit. Now we're going to have a problem here. Okay, and the problem here is when I put this into my equilibrium constant, remember it's hi squared, so it's going to be 0.4 plus 2x squared over 0.1 minus x and 0.05 minus x. I can't just simplify it by any other method. I'm going to have to expand everything out. And then I'm going to have to use a little equation that you might remember. Remember the quadratic equation? Negative b plus or minus square root of b squared minus 4ac all over 2a. What's a, b, and c? Oh, we have to algebra the heck out of this thing, right? Yeah, I'm not actually going to solve this right now, but you are going to have to use the quadratic equation to solve some. I'll solve a quadratic equation for you on the video, but for time's sake, I want to get through a few more things while we're in person. You punching buttons doing a quadratic equation, while it's kind of fun, I'm going to use some other time for it. Okay, so we can use this to calculate equilibrium concentrations. We can use this, and if you want to look in there, using a quadratic expression is fairly simple. Okay, not so simple. It's really easy to lose negative signs as you're doing that. But the last thing I really want to get through while we're in person is what is called LeChatelier's principle. Okay. Now, LeChatelier did go to school, but we're not talking about the guy in charge of his school. What we're going to look at is, let's say I have a reaction that's at equilibrium. If I apply a change to the system will reestablish equilibrium. Now, that may be a instance where the equilibrium is reestablished in seconds. It may take years to reestablish equilibrium. Okay. The speed at which equilibrium is reestablished is irrelevant. We studied that in chapter 14. This is chapter 15. Okay. So it doesn't matter how fast it's going to reestablish equilibrium, just that it's going to reestablish it. And when it does, there's going to be a shift. Okay. So what are some of the things that can affect the equilibrium? Okay. First of all, is addition of a substance. So let's say I have this particular reaction at equilibrium. And if I add some H2, what's going to happen to the equilibrium? It's going to shift to the right. Okay, I'm going to get more products. Okay, very simple. If you look at the equilibrium constant, you'll see why. If I increase the denominator, I need to also decrease that and increase the numerator to re-establish my equilibrium. What if I add some HI, some of our product? It's going to move to the left. Okay. Let me look at a different reaction. Let's say I have this reaction, and I indicated that it is endothermic for a reason. Okay, so there's a number of things that we can do. One of the things that we can do now, why would we want to influence the equilibrium for this particular reaction? Well, this is a very useful product, ammonia. I know some of you like to eat once in a while, maybe not today because it's Ash Wednesday. But our ability to grow food right now, plants can't take nitrogen out of the air. If you see a wheat plant growing, it does not get the nitrogen from the air, okay? Because the nitrogen in the air, side note here, is triple bonded. And it is a very, very, very hard bond to break. So this particular reaction actually can break that nitrogen-nitrogen triple bond and give us nitrogen-hydrogen single bond, which gives nitrogen that's nice and usable by the plants. So it's used for fertilizer quite extensively. It's used for other things too, but it's very extensive use. Okay, there are plants like there's plants that make millions of tons of this on a daily basis, and it's used for. But there's a few things that are done. Now, which of these two do you think is easier to come by, nitrogen or hydrogen? Well, nitrogen is easier to come by. So one of the ways that they can increase the production of it is by pumping more nitrogen into the reaction vessel. Okay. Now, it ensures more use of the hydrogen and it gives us more ammonia. So that's one of the things we can do is we can add that. Now it's exothermic, right? Do I want a high or low temperature? Well, think of heat as a product. And if I add heat, what does that do to the reaction? Okay, it's going to shift the equilibrium the other way, right? Okay. Now, it just so happens that this is run at a fairly high temperature just due to the kinetics of it. So this is the reaction where you get to balance the kinetics and the equilibrium. Okay. If you go too high, equilibrium shift to this side. If you don't go high enough, it takes forever to get over here. So that balance is really important. But there's some other things that can be done. One other thing you can do, you can remove ammonia from the reaction chamber. There's several ways this is done. One simple way of doing it is just to put some H2O there. And this is liquid. The ammonia is very soluble in the water. These two hardly soluble at all in the water. So it removes ammonia from the reaction. Wow, we remove our product. That's kind of what you want to do anyway. You want to take your product out and use it. Okay, but by removing the product, I shift the equilibrium to the right, giving us more ammonia. What about pressure? Well, in this particular case, I have a particular difference in the number of molecules present. My reactants have 4 molecules. My gas has 2 molecules. So an increase in the pressure will shift to relieve that increase in pressure. Now realize if you increase the pressure, you're either adding one or more substance or you are changing the volume. So you are changing the concentration when you do this. But increasing the pressure causes it to shift to the side with lower molecules. So if I put this at a higher pressure, I'm going to get more ammonia. Pretty cool stuff, right? Okay. Now, as a matter of fact, I can actually calculate this. And this is known as a KP, okay? KP is the equilibrium constant and pressure. Now there isn't a equivalence between KP and KC, and I'm pretty sure that's in the book. The derivation of it, maybe the derivation is not in here. Okay, so if you look at the closer look on 560, you're gonna see this exact reaction used for it. The KP is equal to Kc times RT to the delta N. R is the ideal gas constant. And R would have the same unit as the pressure that you're using. So if you're using atmospheres for your pressure, you would use a 0.08206 liter atmosphere per mole Kelvin. If you were using kilopascals, you'd use 8.314. And delta N is the number of moles of gaseous product or reactant, the change in the number of moles. So for this reaction, what's delta N? What's delta N? I heard a couple people try to answer me, but -2. Okay, it's a negative because it goes down 2, so that's going to be important for it. This is an equation which you will use occasionally to relate the pressure and the concentration values. All right, and I think the last thing that we really haven't covered in this chapter, I will go through some more of this in a video. Now, when it talks about the equilibrium, the LeChatelier's principle talks about disturbing equilibrium. It doesn't necessarily call it LeChatelier's principle. I expect you to know it by LeChatelier's principle. If you get a job anywhere, they're going to refer to LeChatelier's principle. You might even hear it mentioned in some of your biology classes, although they may not choose to use that name. But you need to know the name LeChatelier's principle for what happens when you affect a system in equilibrium. Okay. The last thing that I want to go through today, while we have you, okay, for this one, and we're going to go KC, a unwritten subscript is going to be KC. Now this one is NH2 squared H2. What happens if I write the reverse reaction? If I write this one, what's K for this one? Well, this one is going to be how are these two related? They're inverses, right? So if I write the reverse of a reaction, that's the same as K to the -1. Okay, or 1 over K, whichever way you want to write it. So I can do an inverse. I can also do something else. What about this reaction? What is the difference between this one and this one? Well, I multiplied this one by a coefficient of 3, right? I increased all my coefficients by 3. So if I look at this, K is going to be equal to NH3 to 6 over H2 to 9 N2 to the third. Well, this is equal to K to the third power, right? I multiply all of my coefficients by that, all my exponents by that coefficient. raising it to the third power. This is how we can manipulate equilibrium constants. There are going to be some times where manipulating equilibrium constants is going to be very important. We will see some of those next week when we start in on chapter 16. Okay, so we now have, between this and what I will cover in the video for Friday, all of chapter 15 will be covered. We will give you a chance to ask questions. It will either be, let's go, I'll give you some time Monday in class and then some time in the problem session, but I'll give about 15 minutes in class on Monday to answer any problems on homework. And then a little bit of time in the problem session, we'll work on those. But Monday, we are going to start on chapter 16. On Friday, this room is being used for a meeting, and we will not be here in person on Friday. You will have a posted video for that. And we're just going to take tomorrow as, okay, so here is the unofficial official statement about that. Thursday is, you know, for those who had class yesterday, or for those who have class or lab tomorrow, it is your mental health day for the semester for this class. Okay. So we will do that. I may or may not rearrange, well, I'm definitely rearranging the order of the labs since we're doing that. So next week's lab will be the lab originally scheduled for this week. I will rearrange the rest of the labs. It may be that I have us do one lab partially by observation, which is okay because a lot of it's just busy work. I'll make my lab assistants do the busy work. But you may end up doing a part of one lab with another lab. That's okay. It's really not a big deal. I've done that several times. I would like to still leave that last week of class for review. So I'm going to attempt to do some method where we do that. So there's one lab you may do over observation one week and do part of it the next week along with another part. But I will be clear on that. All right. Any questions on lab next week? What are we doing? Okay, it will be cation analysis. That will be next week. Friday, there will be a lecture posted, and I expect you to do the chapter 15 homework. You now have plenty of time to do that, which of course means you guys are going to take a day off and like move off and still not spend time on it. I'm okay with that, but don't forget to do the chapter 15 homework. All right. All right. Well, have a good weekend, everybody. Have a good week. I will see you on Monday.
Yeah. Yeah. Okay. So that was part of. So
notice this. So if you want to,
So those were just part of the same. You were just like, you just increase the coefficients. Okay.
So, what was my question? Oh, for the honors problem,
yes.
you just want me to like send an email to everybody, or we just get to pick groups? Like,
Yeah,
there's a
I
ton
don't
of
care.
us.
There's not that many of you. So if you want to do it all together, if you want to split the two groups, either way.
Okay, I'll just send an email.
And did you guys get the 13 and 14 ones done?
Yeah, I'm pretty sure we're all done with them. We just haven't discussed
Okay.
about them yet.
Okay, I will also have a 15, 16. There will be a separate one over 17, but 15 and 16 all went down before the next test. So I'll send those out. If somebody emails me, I'll send it out to everybody.
Do we know the whole roster?
On the
email everybody. I know.
on the Canvas, you should be able to get to just the honor section on there.
Okay.
And if not, let me know because I don't remember